Hello everyone, welcome to module 1 on intermolecular forces, liquids, solids and phase changes. So let's start with the content overview. In this lecture we'll talk about the overview of a physical states, the type of state that we have and phase changes. Second, we'll discuss quantitative aspects of phase changes. Third, we'll talk about the types of intermolecular forces. Fourth, we'll talk about the properties of liquid state. Fifth, we'll talk about the uniqueness of water, and we'll end this chapter with the solid state, structure, properties and bonding, and finally end with advanced materials. Let's start with phases of matter. So every physical state of matter is generally considered as a phase. So a phase in general is a physically distinct and homogeneous part of a system. The properties of each phase are generally determined by the balance between the potential and the kinetic energy of the particles. So there are two types of energies that are present here. One is the potential energy and the second is the kinetic energy. Kinetic energy in general is generally associated with movement that tends to disperse particles. Potential energy in general is a form of attractive forces that tend to draw the particles together or keep them tightly bound together. So in terms of this potential energy, we'll talk about the type of forces that are present there. There are two types of attractive forces. One is intramolecular forces and intermolecular forces. So focus on the word intra and inter. So whenever you see the word intramolecular forces, this is between. So this is inside the molecule. Intermolecular means between molecules. So intramolecular forces are also called bonding forces, and intermolecular forces are also called non-bonding forces. So intramolecular forces are generally forces that are found within a molecule, and these are basically due to the chemical behavior of each phase of matter that is present, and it generally is the same because the same constituent particles is present in each case. For example, if you take H2O molecules, the H2O molecules are present whether the substance is in any phase, right? So the intramolecular forces are found in every single phase of a system, but what changes is the forces between molecules in that kind of a phase change. So let's take the example here of intramolecular forces. So intermolecular forces are non-bonding forces that are found between molecules. So the physical behavior of each phase of matter is generally different because the strength of these forces differs from state to state. So remember this, that when the phase changes, the amount of intermolecular force also will change. Let's talk about a macroscopic comparison of all the states of matter. Let's start with the gas. So let's first start with the shape and volume. Gases in general, they conform to the shape and volume of the container, and they have really high compressibility and they have really high ability to flow because of high compressibility. Liquids, they conform to the shape of the container, but the volume in general is only limited by its surface. So however higher is the surface, that limits the amount of volume that it can occupy. And when you take compressibility, it generally is very low and it has a moderate ability to flow because it can only flow until a certain extent where its viscosity can overcome the friction. After that, it does not flow. Next, the final substance is solid. Solids generally have their own shape and volume, and they have no compressibility at all because they cannot be compressed. Even under application of pressure, you cannot reduce the volume of a solid, and they have almost no ability to flow because remember that these are packed materials. They do not have any kind of an ability to flow. Let's take a kinetic molecular view of these three states of matter between the type of attraction force that they have and the properties that they exhibit. Let's take gases. In gases, the attractive forces in general are relatively weak in relative to the kinetic energy because particles are always randomly moving around. And what properties that give? So that makes the particles very far apart because there is no attractive forces, and makes the gas having no fixed shape and volume. Let's take the example of a liquid. In liquids, the attractive forces are stronger because the particles in general have less kinetic energy. This makes the liquid flow and change shape, but makes it have a fixed volume. Let's take solids. Solids, they only have attractions that dominate their motion because particles here are fixed in place and there is relatively no minuscule kinetic energy. And a solid in general has a fixed shape and volume. Notice that what you're noticing is that as the attractive force starts increasing, you start noticing that the molecules are much more orderly. Let's say the word orderly. So as the higher the attractive forces, the more orderly the material. So the phase of matter actually depends on, the amount of attractive force that is present inside that particular material. Now let's discuss phase change. We have three phases of matter, and we'll try to discuss what each type of phase means. So when a solid converts to a liquid, we call it melting, or we also call it fusion. And when a liquid turns into a gas, we call it vaporization. And in reverse, gas turning into a liquid is called condensation. And a liquid turning into a solid is considered freezing. In the same way, a solid can turn into a gas. We call it sublimation. In the same way, a gas can also turn into a solid. So the common example of this is if you take carbon dioxide as ice crystals, they generally deposit. So it's called deposition. Now the process of converting a solid into a gas is generally endothermic process. So all of these processes above, melting, vaporization, all of them need energy for them to occur. But the reverse processes, condensation and freezing, both of these are exothermic processes because they release energy in reverse. Notice that the phase change and the type of energy change that happens here. So because it's exothermic, delta H is less than 0 here. Because it's endothermic, delta H is greater than 0. But what does that delta H actually mean here? So let's take an example of two familiar phase changes. One of them is deposition. So when you look at deposition, example of a deposition is look at on a snowy day. On a snowy day, you're actually noticing that the water vapor in the air is directly converted into ice particles, which is coming down to the earth as snow. So snow is basically a good example of deposition because the water vapor is being converted directly into ice. Vaporization is where you have water molecules being converted into vapor. An example of this is perspiration. So perspiration is an example of understanding how your body converts sweat directly into vapor. So these are heats of vaporization and fusion for several materials. So let's take examples. Notice that the vaporization and fusion, notice that the vaporization value is generally higher in comparison to the fusion value because it takes a lot more energy to vaporize than it takes a lot more energy to fuse. So we noticed all the fundamental changes that are happening here. Let's take the example here. First, the amount of heat that is needed to convert a solid into a liquid is called delta H of, so enthalpy of fusion. And the amount of energy that is needed to convert a liquid into a gas is called enthalpy of vaporization. And the reverse is negative delta H of vaporization is the enthalpy that is required for condensation. And freezing is the negative of fusion. Sublimation is the combination of both delta H of fusion and delta H of vaporization. Deposition is also the negative of sublimation value. The energy does not change, but only the sign will change. Let's start about the quantitative aspects of phase change. So we talked about the qualities of phase change where the phase will change from solid to liquid, liquid to gas. But let's now talk about how and what is the amount of quantity that is required to phase change. Now there are two types of heats that are required. One is within a phase and the other is during a phase change. So within a phase where you have where the structure is either a liquid or a solid or a gas, the heat flow here is accompanied by a change in temperature. Since the temperature increase is generally caused due to the average kinetic energy of the particles will change, which causes the molecules to adjust its energy by raising the temperature. So the formula for that is Q equals amount times heat capacity times delta T. Delta T here mentioning the change in temperature. Whenever a phase change is occurring, where you have phase change happening from solid to liquid or liquid to gas, heat flow here generally does not change the temperature while the temperature remains constant, because what is happening here is that during a phase change the heat flow is generally used to change the average distance between the particles and between the particle changes. So understand that here during a phase change we are manipulating the intermolecular distance, and within a phase we are basically changing the kinetic energy of the particles. So kinetic energy is manipulated within a phase and potential energy is being manipulated during a phase change. So for that, during a phase change, Q is given by the amount of material into delta H of the phase change, so enthalpy of the phase change. Let's take the example of a cooling curve of gaseous water that is being turned to ice. So let's say we're starting with stage 1 where we have gas particles that are freely moving around, and we are slowly moving the gases, slowly cooling the gas particles. So these gas particles, they will start moving until they will start losing energy until they reach 100 degrees. At 100 degrees, they stay at a constant temperature for a long time. Why? Because at that point, they turn into a gas-liquid mixture where the gas particles try to lose energy and start depositing on the surface and forming a liquid. So what is happening here is that the randomly moving kinetic energy of the particles is being converted into the loss of energy is being compensated by creating the attraction forces between the molecules. So these molecules will start attracting each other and forming the liquid gas mixture. This happens until all of the gas molecules are converted to liquid, and at this point all of the gas is converted to liquid and it's in a single phase. Now this single phase again starts to lose energy more and more, and once it reaches 0 degree centigrade, again it becomes a constant temperature. The constant temperature again lasts a longer time because the arrangement now is trying to make the molecules get a shape. Before it was trying to create the attractive forces, now the molecules will try to conserve more and more energy. As they lose more and more energy, they start attracting towards each other more and more, and they start packing themselves into solid structures. And at this point where you have a liquid, so it starts creating a liquid solid mixture, and this phase continues. It stays at a constant temperature until all of the liquid is converted into a solid, and at this point once it converts into a solid where it freezes into ice, again it starts lowering temperature and going downward. Notice that here these two phases are where there is a phase change. So because it has a constant temperature, the energy that is used here is delta H of vaporization in gas liquid phase change is being used to convert gas into a liquid where it loses this energy. So it does not lose the actual temperature, it actually loses this delta H of vaporization, and in conversion from liquid to solid it loses this energy, delta H of fusion. So this energy is being released out of the system during the phase change. So this is the idea behind a cooling curve for the conversion of gaseous water to ice. So remember that it only happens at two temperatures. At 100 degrees centigrade, gas liquid phase change occurs, and at 0 degrees centigrade, liquid solid phase change occurs. Now let's try and understand this question here. So the scenes below represent a phase change of water So select data from the previous text discussions to find the heat in kilojoules released or absorbed when 24.3 grams of H2O undergoes this change. So they are converting 85 grams of water into 117 grams of water vapor. Now they're asking us to calculate whether the energy is being released or absorbed. So first thing that we need to know is what is the amount of energy that is being, the enthalpy of vaporization and enthalpy of fusion. So for water, the value for vaporization is 40.7 kilojoule per mole and fusion is 6.02 kilojoule per mole. So let us write down the data that is given here. So you have delta H of vaporization, which is 40. So the value is 40.7 kilojoule per mole, and delta H of fusion is 6.02 kilojoule per mole. So the starting mass is 20 to 24.3 grams. So mass of H2O. Now, from the data that we have here, so what is the extra data that we need here? First thing we need to know is what is the specific heat of water. So specific heat of water from the data before. The specific heat changes with phase as well because we are in the liquid phase. So the specific heat of water in its liquid phase is 75.4 kilojoules per mole degree centigrade. So that's the value for the specific heat of water. Now let's take the idea here, what is happening here in terms of the phase change. So first we are starting at 85 degrees centigrade, and notice that at 85 degrees centigrade it's still water, because notice that here it changes into. So first what happens, so there is a constant rise in temperature until 100 degrees centigrade, and at 100 degrees centigrade so there is a constant rise in temperature until 100 degrees centigrade, and at 100 degrees centigrade it lays flat, and again it reaches 117 degrees centigrade. So let's say that this is 117 degrees centigrade, this is 100 degrees centigrade where it is constant phase, and at the start you have 85 degrees centigrade. So notice that what is the first phase change that occurs. So this is the first phase that has to happen. So this stage, and this is the second stage, and this here is the third stage. So we have three stages that are happening here. So this is the first stage. So here, what will be the heat here? So let's consider this Q1 and this part to be Q2 and this part to be Q3. Here we are still in water phase, we are still in the liquid phase. Here we are in the liquid vapor mixture, and finally we are at the vapor stage. Now let's consider each of these considerations here for liquid, liquid vapor and vapor. First let's take liquid. So the specific heat of water when it was liquid is given here, and the specific heat of water when it's a gas is 33.1 joule per mole degree centigrade. So first thing that we need to find is Q1. Let's start with Q1. How will you find Q1 here? So we know that Q here is mc into delta T. So for here, so the mass of water, so mass of H2O as a liquid, and C of water as a liquid, into the temperature change that happens during Q1. So during Q1, the temperature change happens until 100 degrees. So it starts at 85 and ends at 100 degrees. So delta T here is always the change in temperature, the final temperature minus the initial temperature. So the mass of H2O here, how would you calculate the mass of H2O here? I'm sorry, here we need the number of moles of H2, N, the amount we need N. So N of H2O, how do you calculate the number of moles of H2O? So mass of H2O by the molar mass of H2O. So the mass of H2O in the problem is 24.3 grams divided by the molar mass of H2O. So how would you find the molar mass of H2O? Hydrogen times 2 plus 1 times oxygen. So 1.008 times 2 plus 1 times 16.00. So we have 2.016 plus 16.00. So which becomes 18.016, which when you round it off to the significant figures becomes 18.02 gram per mole. So this is going to be 18.02 gram per mole. So use a calculator and find the exact value. So we have 24.3 divided by 18.02. So that gives you an answer of 1.348 mole. So we only needed to 3 significant figures. So when you round it off, you get 1.35 mole. So the number of moles of H2O is 1.35 mole. So you have 1.35 mole times specific heat of water when liquid is 75.4 joule per mole degree centigrade times the temperature change, which is Tf minus Ti. Tf is 100. So times 100 minus 85. Again, use the calculator, calculate the value. We have 1.35 times 75.4 times 15. So it becomes 1526.85 joule, so which is Q1. So when you convert it into kilojoule, it becomes 1.53 kilojoule. So this is Q1. So we found Q1. So this is the value we found. We need Q2. Notice that Q1 is increasing temperature. Q2 is phase change happening from liquid to vapor. So because it's a phase change, so Q2, the formula becomes amount times the delta H of phase change. So the phase change that is happening here is vaporization. So amount here will stay the same, N of H2O. Notice that number of moles will not change even if the phase changes, times delta H of vaporization. So which is 1.35 mole times delta H of vaporization from the values is 40.7 kilojoule per mole. So calculate the value, 1.35 times 40.7, so which gives you 54.945 kilojoule. So this is mole times kilojoule per mole. So mole get cancelled. You get the value for Q2. Again Q3, it's a phase change. It's not a phase change. It's just a increase in temperature. Vapor increases from 100 to 117 degrees. So which is going to be again N times C times delta T. So N of H2O times C of H2O, because here it's vapor, so you have C of H2O of gas times delta T. Again 1.35 times C of H2O when it is gas. So this data will all be given in the questions. Always don't need to worry about this data. So that value is 33.1 times delta T is 117 minus 100. So find the value. You have 1.35 times 33.1 times 17. So that is 759.64 joule is Q3, because we are writing all of them in kilojoules. So this becomes 0.76 kilojoule. So we have all the values. So what is the Q total? Q total will be Q1 plus Q2 plus Q3. So Q1 value is 1.53 plus 54.94 plus 0.76. So when you add everything up, you have 1.53 plus 54.94 plus 0.76. So the entire answer will become 57.23 kilojoules. So this is the total energy change. Now notice that here we have to know whether this energy change is going to be absorbing or releasing. Here we are converting a liquid into a vapor. So here the phase is being converted to liquid to vapor, which is vaporization, which is an endothermic process. So here Q will be absorbed. So the energy is being absorbed. So the energy here is being absorbed. So this is the idea here of the problem and how do you convert values. So remember that whenever it's a phase change, we use the enthalpy of fusion or vaporization. Whenever it is temperature change, we are changing the value from. So we are changing whether it is, we are choosing whether it is water, specific heat and temperature change. So this is how you can solve a problem that involves temperatures. Next, let's discuss vapor pressure. So vapor pressure is a point that we generally discuss under the topic of liquid-gas equilibrium. So what happens when you have a liquid and a gas interacting with each other? So let's consider molecules in a vacuum jar. So we have an evacuated jar that contains a liquid. So what happens when there is vacuum is that the molecules try to occupy more space. Because there is an empty space, the molecules try to go up and up. So what happens at this point is that liquid will vaporize for a moment, and those liquid molecules will try to hit the water molecules, causing the liquid molecule again to vaporize. Again, hitting vaporization. So this continues until the rate of vaporization is greater than the rate of condensation, and at a certain point it reaches an equilibrium. So that equilibrium point, so in a closed flask, the system generally reaches a state of dynamic equilibrium, so where the molecules leaving and entering the liquid are at the same rate. So the vapor pressure is basically the pressure that is exerted by the vapor on the liquid, and this general pressure increases until a certain equilibrium is reached, and at equilibrium this vapor pressure becomes constant. So what happens when you increase the temperature? So the effect of temperature is generally very high on the distribution of the molecular speeds. So when you increase temperature, there is more number of molecules that are at a higher speed, and at a certain point the molecules are moving generally fast enough to vaporize, so they do more at higher temperatures. The higher the temperature, so the kinetic energy in general, this is the point where the kinetic energy is needed to overcome the intermolecular forces that are in the liquid. So let's talk about the factors that affect the vapor pressure. So the number one factor that affects this is the temperature. So as the temperature increases, the fraction of molecules with enough energy to enter the vapor phase will also increase, thereby increasing the vapor pressure as well. So the higher the temperature, the higher the pressure. Next, the weaker the intermolecular forces, the more easily the particles enter the vapor phase and higher the vapor pressure. So when the forces are weaker, the vapor pressure is higher. So how do you write vapor pressure as a function of temperature and intermolecular forces? So as you notice here, as the temperature increases, the vapor pressure will increase. At atmospheric pressure, so when the vapor pressure is 760 torr, so that is the point where water generally evaporates at 100 degrees centigrade, ethanol evaporates at 78.5 degrees centigrade, and diethyl ether evaporates at 34.5 degrees centigrade. So as the temperature becomes higher and higher, so when you have lower vapor pressure and lower temperature, so the lower the vapor pressure, then there is a chance that the material can evaporate at lower temperatures. For example, if you have a vapor pressure of 500 torr, then water can evaporate at around 90 degrees centigrade. So vapor pressure is an important factor in consideration for boiling point. So as the vapor pressure increases, the temperature will increase. So the vapor pressure will decrease when the strength of the intermolecular forces starts to increase. So this is an example where you take water here. Water has a lot more intermolecular forces than ethanol and diethyl ether. That's the reason why its vapor pressure in general is much lower. So as the vapor pressure will decrease when you have higher intermolecular forces. So one of the important equations that can be used to write down the vapor pressure is the Clausius-Clapeyron equation. So this is the equation that relates the vapor pressure to the temperature. So log of P is minus delta H of vaporization by R times 1 by T plus C. So the 2-point form is the one that is used to when you have vapor pressures between two temperatures. So ln2 P2 by P1 equals minus delta H vaporization by R times 1 by T2 minus 1 by T1. So where R is 8.314 joule per mole Kelvin, which is still the universal gas constant. So when you write the same equation in a graph, you notice that the graph is a linear graph where you plot the graph of y ln and 1 by T. The slope here is the minus delta H vaporization by R. For water is much more steeper. For diethyl ether, it's much more broader. Now, so let's consider an example here. So the vapor pressure of ethanol is 115 torr at 34.9 degrees centigrade. If the delta H of vaporization is 38.6 kilojoule per mole, so they're asking us to calculate the temperature in degrees centigrade when the vapor pressure is 760 torr. So how do you solve this equation? First, convert all the temperatures into Kelvin. So we have 34.9 degrees centigrade, so which in Kelvin becomes 34.9 plus 273.15. So we have 34.9 plus 273.15. That gives you a value of 308.1 Kelvin. So it's just three significant figures. So we have 308.1 Kelvin. Next, we have vapor pressure. So the vapor pressure is written as P is 760 torr, and the vapor pressure, initial vapor pressure, so this is P2. P1 is given as 115 torr, and P2 is given as 760 torr. You have delta H of vaporization of ethanol is 38.6 kilojoule per mole. Now, so based on the values that we have here, they are asking you to judge the temperature. So this temperature is T1. They are asking you to calculate T2. So use the Clausius-Clapeyron equation. So we have the Clausius-Clapeyron equation for two temperatures, which is ln P2 by P1 equals minus delta H of vaporization by R times 1 by T2 minus 1 by T1. So we have all the values that we need. We have P1, P2, and we are going to need to convert the values here, 760 torr and 115 torr. Notice that these are the same units and it's a ratio, so we do not need to convert units here. So we can directly write the value directly here. So ln of 760 by 115 equals minus delta H vaporization is given as 38.6 kilojoule per mole. So this becomes 10 cube by R is 8.314 joule per mole Kelvin, and times 1 by, so the value that we don't know is T2, minus 1 by T1 is 308.1. So when you calculate the value, so that becomes ln of 760 by 115. So this value of ln of 760 by 115 gives you a value of 1.88. So let's consider this 1.889. So 1.89, and this equals, you have 38.6 times 1000 divided by 8.314. So that gives you minus 4642.77 times 1 by T2 minus 1 by 308.1. So now take this to the other side. So you have 1.89 over minus 4642.77 equals 1 by T2 minus, now let's calculate 1 over 308.1, which gives you a value of 0.003245. Now we need 1 by T2. So let's calculate first 1.89 divided by 4642.77. So that value becomes minus 0.0004070 is equal to 1 by T2 minus, the value is 0.003245. So now 1 by T2 becomes 0.003245 minus 0.0004070. So 1 by T2 becomes 0.002838. Now we need T2, so T2 becomes 1 over 0.002838. Now inverse of that value is 352.37 Kelvin. So if you want to convert it into degree centigrade, so 352.37 minus 273.15, so the value is 79.22 degrees centigrade. So this is the temperature at which the vapor pressure is 760 torr. So this is the temperature at which the vapor pressure becomes 760 torr. So this is how you solve problems using the Clausius-Clapeyron equation. Next, let's talk about vapor pressure and the boiling point. So the boiling point of a liquid is the temperature at which the vapor pressure equals the external pressure. So this is an important point to remember. So boiling point is not decided by any other quantity other than the vapor pressure of the liquid. So the boiling point of liquid is basically the temperature at which both the vapor pressure becomes equal to the normal pressure. So when the vapor pressure equals to the external pressure, the temperature at this point is called as the boiling point. So this is an important point. So because the normal boiling point of a substance is generally observed at the standard atmospheric pressure or 760 torr. So when you increase the external pressure of the liquid, automatically the boiling point will start to increase. That's the reason why even if you put it into a pressure cooker, if you look at cooking in a pressure cooker, you will notice that the vegetables that you put in a pressure cooker boil at a higher temperature because there is still water at that temperature because of the presence of higher vapor pressure. Because you've increased the external pressure, automatically the vapor pressure will also increase. So let's look at the example of a phase diagram. So phase diagrams are an excellent way of looking at the vapor pressure. They're looking at how phase change generally occurs. So phase change in general, you'll notice that at lower temperatures, it's still a solid. So as you try to increase the temperature, it starts to convert into a liquid. And at a certain point, it crosses the critical point and then converts it into a gas. So one peculiar characteristic of water is that water generally has a negative density, which means that the liquid here is denser than the solid. So this is very rare and very rare in substances, and that's the reason why ice floats on water. This is one of the reasons why ice floats on water. When you take the same thing with any other solid, it doesn't happen the same way. The only reason why ice floats on water is because of the presence of lesser density than water itself. So liquid here is denser than the solid. This negative slope is what makes ice float on water rather than sinking it into the entire water. Another important point to remember is the triple point. So triple point is the point in the phase diagram or the condition of 0.0 degrees centigrade and 0.006 atmosphere, at which all three phases coexist at the same time. So all the three phases exist simultaneously. So this is the point where all three phases will exist simultaneously. So where you have a solid, you have a liquid and a gas at the same point of time. Another point to remember is the critical point. So critical point is the point where it stops becoming a liquid and it becomes a gas. So this is the exceeding point where once you cross that point, there is no coming back. The phase is completely gaseous. So the completely gaseous, and it crosses the vapor pressure point. So that point is 374 degrees centigrade and 218 atmosphere. So let's look at other phase diagrams. So this is the phase diagram of methane, where you notice that you have a supercritical fluid. So supercritical fluid is a fluid where once you cross the critical point, it becomes a liquid and a gas at the same time. So that mixture is generally called as a supercritical fluid. This is a phase diagram for carbon dioxide. At the critical point here, the densities of the liquid and the gas phases will become equal. At that point where you'll notice that the material will start to behave like a fluid. So this is the critical point where it starts to behave like a fluid. So the pressure of the liquid is equal to the density of the liquid becomes equal to the density of the gas. So that point is generally called as the critical point. So let's take a simple example of a problem. So here they are giving us the phase diagram of carbon, and they're asking us to describe the phases and the changes that a sample of carbon undergoes under the following processes. First, the sample is heated to 10 square bar from 1000 Kelvin to 5000 Kelvin. So we are starting at 1000 Kelvin. So we are starting at 1000 Kelvin, point A, and from point A we are going to 5000 Kelvin, and we are increasing the pressure to 10 square bar, which is about 100. So this is about 5000 Kelvin here. So this is the point there. So this is the phase change that is happening there. Notice that this is the point where, so that's the point where we are starting about the triple point of carbon. So where solid, liquid and gas, it exists at the same time. Then the sample is compressed at 5000 Kelvin to 10 power 6 bar. So from here we are going to 5000 Kelvin at 10 power 6 bar. So we are going to 10 power 6 bar. Once you go to 10 power 6 bar, you are converting it into a solid. So this is one of the coolest parts about carbon, is that carbon has two solid phases. One is graphite and one is diamond. And diamond generally exists at high pressures and high temperatures. So when you have really high pressure and really high temperature, that is the point where the graphite carbon converts it into a diamond carbon. Next, let's discuss the nature of intermolecular forces. So we discussed what are the type, what are intermolecular forces, what do they do, and what are the characteristics of different phases of it. So intermolecular forces generally arise from the attraction between the molecules. This attraction is generally between the partial charges or between the ions and molecules. So the three types of forces that can interact. One is between the partial charges between the molecules with partial charges, ions, and molecules themselves. Now, these intermolecular forces are generally relatively weak compared to the bonding forces because they involve smaller charges that are really far apart. So let's take an example of this. The first one we're going to discuss is covalent and van der Waals radii. So the van der Waals distance is the distance between two non-bonded atoms in adjacent molecules. So when you have two non-bonded atoms, the distance between the two molecules is considered as the van der Waals distance, and half of that distance is considered as the van der Waals radii. Now remember the difference between covalent and van der Waals radii. Covalent radii is the radii inside the molecule. Van der Waals radii is the radii between the molecules. So between two separate molecules, covalent radii is the distance between the half of the distance between the molecule in itself. Intramolecular distance and intermolecular distance. Now let's take a periodic trend of covalent and van der Waals radii. As you notice that as you go down the period, the van der Waals radii generally tries to increase. As you go down the group, the van der Waals radii increases, and across a group, the van der Waals radii generally decreases. So this is the idea behind van der Waals radii. Now let's try to compare bonding and non-bonding forces. So first we'll talk about bonding forces. So bonding, there are three types of forces: ionic, covalent, and metallic bonding. So in an ionic bonding, the ionic forces are generally between the negatively and positively charged ions. The basis of attraction here is the cation-anion attraction, and this has the highest amount of energy, ranging from 4,400 to 4,000 kilojoule per mole. An example of this is NaCl, sodium chloride. Covalent molecules generally get their attraction force between the nuclei shared electron pair. This is relatively moderate with about 150 to 1100 kilojoules per mole. An example of this is hydrogen, H2. And metallic bonding generally comes because of the cations and delocalized electrons. They have really less energy, ranging from 75 to 1000. An example of this is iron. Now let's compare non-bonding forces. Non-bonding forces, there are 6 types. First one is Ion-Dipole, where the attraction is between an ion charge and a dipole charge. They range around 40 to 600 kilojoule per mole. Generally are between metals and polar molecules. So ions and polar molecules. Next we have hydrogen bonds. Hydrogen bonds generally range because of polar bond to hydrogen and dipole charge. So of high electronegative elements of nitrogen, oxygen and fluorine. Generally range from 10 to 40, generally found in polar molecules. Dipole-dipole forces, where you have two different polar molecules. Ion-induced dipole, where you have an ion charge that induces a dipole in a non-polar molecule. You have a dipole-induced dipole, where a dipole induces a charge in a non-polar molecule. And you have dispersion forces between two molecules, which are basically due to polarizable electron clouds. These are generally due to their size. Let's start with the first type, polar molecules and dipole-dipole force. When you take a solid in a polar molecule, the polar molecules generally try to adjust their domain in the same direction to make sure they facilitate the structure, creating this structure. And always remember that the positive pole of one polar molecule attracts the negative pole of the other. So this thus creating the polar non-polar interaction. Now, one of the main characteristics that decides the structure is the dipole moment. The higher the dipole moment, the higher the boiling point. So the higher the boiling point, the more stable the molecule. So when you take the example of, for example, say acetonitrile, acetonitrile generally has a lot higher 392 3.92D dipole moment, thereby giving it a boiling point of 355. So notice the trend here. As the dipole moment increases, there is an increase in the boiling point of the material. So molecules with the greater dipole moments attract each other more, so therefore boil at higher temperatures. Next, let's discuss the hydrogen bond. So hydrogen bonding is only possible for molecules that have a hydrogen atom. Remember this, the first requirement that is needed is it should have a hydrogen atom that is covalently bonded to a small, highly electronegative atom with lone electron pairs. Specifically, either nitrogen, oxygen, or fluorine. So what are the two requirements for a hydrogen bond? Number one, you should have hydrogen atom in the molecule. Number two, this hydrogen atom must be bonded to a highly electronegative element. Most commonly, this highly electronegative element should have with lone pairs. Most commonly, these are nitrogen, oxygen, and fluorine. So an intermolecular hydrogen bond is basically an attraction between the hydrogen atom of one molecule and a lone pair of the nitrogen, oxygen, or fluorine of another molecule. So for example, here the hydrogen here and the electron pair of the fluorine, hydrogen here and oxygen, hydrogen here and nitrogen. So this is how hydrogen bonds generally work. So let's take an example here and notice based on the trend what would be this molecule. Based on the trend here, you notice that this molecule is H2O. So notice that HF and NH3 have higher energies, the higher boiling points than other atoms. The main reason is because of the presence of hydrogen bond in all of these molecules. So because of the presence of hydrogen bond in all of these molecules. While CH4 does not have this, that's why it has a lower boiling point. So because CH4 does not have no hydrogen bonds, because carbon is not a highly electronegative element. Now, they are asking you which of the following substances exhibit hydrogen bonding. So for any that do, they are asking you to draw the hydrogen bonds between two of its molecules. So first you have C2H6. C2H6 has hydrogens, but the hydrogen here is not bonded to nitrogen, oxygen, or fluorine. So C2H6 does not have any hydrogen bonds. Next you have CH3OH. So based on the Lewis dot structure, which you have learned in the last inorganic one, try to draw the Lewis dot structure for CH3OH. You should get a structure that looks like this. Now, what are the requirements? First, there should be a hydrogen atom. Second, that hydrogen atom should be bonded to nitrogen, oxygen, or fluorine. So here it's bonded to oxygen. So that's excellent. So we can show here how would we write down the structure here. So this is the bond and this is the bond. So these are the two bonds that are being exhibited here. So you have these two here are the hydrogen bonds. So this is the requirement for a hydrogen bond. First, there should be a hydrogen atom. Second, that hydrogen atom should be bonded to nitrogen, oxygen, or fluorine and have a lone pair. Next, you have CH3, C double bond NH2. So let's try to draw that structure. You have CH3, C double bond NH2. So CH3 can be written as next we have C double bond O with two lone pairs and nitrogen with two hydrogens. and a lone pair. Notice that there is no hydrogen bonded to this oxygen, so there is no hydrogen bond here. So the only hydrogen bond that is present here would be with this nitrogen and these two hydrogens. So these two hydrogens will bond with another similar molecule. So let me copy this entire molecule so that we can use this. So the bonding comes so let me put it here first, so that let me take this out. So the bond comes right here. So this is the bond that you can get between for these molecules. So there is a hydrogen bond here. The hydrogen is bonded to a nitrogen. Nitrogen has a lone pair. So therefore, this is the hydrogen bond. So this is how hydrogen bonds work in a molecule. So this is how molecules generally have hydrogen bonds. Next, let's talk about polarizability and induced dipole. So what's an induced dipole? So remember, the term dipole generally comes from the fact that it's a polar molecule. Now, when you have a polar molecule nearby, which generally creates an electric field, it can induce a distortion in the electron cloud of an atom or ion of the molecule. So when you have a non-polar molecule, it induces a temporary dipole, and for a polar molecule, the field enhances the existing dipole moment. So the polarizability of a particle is the ease with which its electron cloud is distorted. So whether it is easily distorted or whether it requires a lot more energy to get distorted. So what are the trends in polarizability? So the smaller the particles, the less polarizable than the larger ones, because their electron clouds are held more tightly. So when you increases down a group, polarizability generally increases down a group because the atomic size increases, and you have larger electron clouds that can distort more easily. But it decreases across a period because of the increasing effective nuclear charge, which decreases the size of the atom. Now, cations are smaller than their parent atoms and less polarizable. Anions generally have higher than their parent atoms, more polarizable because they are larger than their parent atoms. Next, let's take the example here of dispersion forces among non-polar molecules. So when two atoms are far apart, they do not influence one another. But when atoms are close together, the instantaneous dipole in one atom tries to induce dipole in another atom. So it basically converts a non-polar molecule into a polar molecule because it becomes closer and closer to a polar molecule. This process occurs throughout the entire sample, creating a dipole-induced dipole force. It creates a force called dipole-induced dipole force. So one dipole tries to induce a dipole in a non-polar molecule. So that is dipole-induced dipole force. Next, the last one is dispersion forces. Dispersion forces are generally called London forces. These arise when you have an instantaneous dipole in one particle that induces a dipole in another, resulting in an attraction between them. So these dispersion forces exist between all particles, increasing the energy of attraction in all matter. These dispersion forces are stronger for more polarizable particles. So therefore, larger particles experience stronger dispersion forces than smaller ones. So the dispersion forces are generally stronger for larger and more polarizable atoms. So as the polarizability increases, there is an increase in the dispersion force. Let's take an example between two molecules, N-pentane and neopentane. N-pentane has a larger surface area. So the larger the surface area, the more more easily its electron cloud can be distorted, thereby increasing the dispersion force. So because there is more points where it can be dispersed, this is the place where it can undergo more dispersion forces. But for neopentane, there is less surface area, so there are fewer points where dispersion forces can act, so therefore it has lesser dispersion forces. Even though the molecule has the same number of carbons, the same number of hydrogens, the molecule by itself does not have a higher dispersion force because it does not have a higher surface area. That's the reason why N-pentane has a boiling point of 36.1, while neopentane has a boiling point of 9.5 degrees centigrade. So the higher the dispersion force, the higher the boiling point. This is the common idea between the structures. So how would you determine the intermolecular forces in a sample? First, consider the interacting particles, whether it's atoms, molecules, or ions. If there are ions present, and if there are only ions present, then the interaction directly comes from ionic bonding. If the ions were present with polar molecules, you end up with ion-dipole forces. If there are no ions present, the number one thing we have to consider is that there is any polar molecules. If there are polar molecules, the forces are dipole-dipole forces, and if those dipole-dipole forces have a hydrogen bonded to a nitrogen, oxygen, or fluorine, you get hydrogen bonding. If there are only non-polar molecules, you have dispersion forces only, and if you have a mix of polar and non-polar molecules, you get dipole-induced dipole forces. Remember that dispersion forces are present in every single molecule in any interacting particles because of their size. So dispersion forces are mainly present because of their size and instantaneous dipole creation. So use these principles now and try to determine, so pause the video right here and try to determine what are the types of intermolecular forces and each of them. So let me do the first one. So you have MgCl2 or PCl3. So which have the higher boiling point. So the higher the intermolecular force, the higher the boiling point. Notice that MgCl2 is Mg2 plus and 2Cl minus. So this is an ionic molecule. So these are ions, which means that this is basically an ionic bonding. So which means this has a higher boiling point. So the higher the grade, the higher the boiling point. Use the same principle again between CH3NH2 and CH3F. So between CH3NH2 and CH3F, try to determine which of these molecules generally ends up creating the structure. So in B, notice that CH3NH2 has a hydrogen bond because the hydrogen is bonded to nitrogen. Here, there is no hydrogen bonded to fluorine directly, so therefore this does not have a higher boiling point. So this has a higher intermolecular force, so therefore this has a higher boiling point. So this way, try to determine across all the molecules which of these have higher boiling points and which of these are generally the structures that give you more higher boiling points. So pause the video right here and try to determine the molecules. Next, let's look at C here. C, you have CH3OH or CH3CH2OH. Now, in CH3OH, you have a hydrogen bond, and CH32OH, we also have a hydrogen bond. But notice that both of them also have a same number of hydrogen bonds. But the difference here is that CH2OH is a larger molecule, therefore has higher dispersion forces. So creating a more dispersion force in one molecule with the added hydrogen bond. So therefore CH3CH2OH will have a higher boiling point than CH3OH. Next, D, you have hexane and 2,2-dimethylbutane. Hexane has a larger surface area in comparison to 2,2-dimethylbutane, thereby creating a higher boiling point for hexane than 2,2-dimethylbutane. So this is the idea, because notice that these are both of them are non-polar molecules and they cannot have any dipole, so the only forces are dispersion forces. So there is higher dispersion forces for hexane. So the dispersion forces are higher for hexane, thereby resulting in a higher boiling point for hexane. So this is the idea behind the intermolecular forces. Next, let's discuss the uniqueness of water. The first one is the molecular basis of surface tension. So when you have a surface molecule, in general, when you take two water molecules, one is the surface molecule and one is the molecule in the interior of the liquid. A surface molecule generally experiences a net attraction downward. This causes a liquid surface to have the smallest area possible, thereby creating a surface. So without surface tension, there is no possibility of creation of a surface. But the interior molecule has been attracted on all sides, so therefore is more stable. So the surface tension is basically the energy required to increase the surface area of a liquid. So the stronger the forces between the particles, the higher the surface tension. So among molecules, you have diethyl ether, ethanol, 1-butanol, water, and mercury. So diethyl ether has the major forces required resulting in surface tension are dipole-dipole and dispersion forces. For ethanol, it's a hydrogen bonding. For water, it's also hydrogen bonding. For 1-butanol, it both compensates hydrogen bonding and dispersion. For mercury, it's fully metallic bonding. Next one is capillary action. Capillary action generally requires understanding of two forces. One is cohesive forces and adhesive forces. Cohesive forces are the forces between molecules of similar type. Adhesive forces are the attraction between molecules of different types. Now, if the adhesive forces are greater than the cohesive forces, the meniscus will be upward. So the meniscus generally will have an upward shape. But if the adhesive forces are less than the cohesive forces, the meniscus will have a downward shape. For water, you will see an upper meniscus. For mercury, you will see a downward meniscus or a convex meniscus. This is due to the presence of the adhesive and cohesive forces. And this is the reason why water exhibits a capillary rise. When you put it in a small tube, it rises. When you see a mercury, when you put it into a big jar, when you have a small tube, put it into a big jar, you will notice a capillary fall. Now, so these are the properties. So the atomic properties of oxygen and hydrogen result in the molecular properties of H2O, and the molecular properties of H2O result in polarity. The polarity is due to hydrogen bond, results in hydrogen bonding. The hydrogen bonding then creates solvent power, which can make it easily dissolve ions in seawater, fresh water, and cellular liquid. It can dissolve carbon dioxide for coral reefs and plants. It has dissolved oxygen for animals, and it has dissolved sugars and proteins in cells. It also has higher heat capacity and higher heat of vaporization, resulting in a narrow range of body temperature, narrow range of Earth's temperatures, natural water cycle, and winds and storms. And this hydrogen bonding also creates surface tension and capillarity, which results in life on lake and soils, and water in soil for plants. The open structure of ice results in the survival of lake life in winter, the nutrient turnover in lakes, and the formation of sand and soil. So this is the uniqueness of water. Next, let's discuss the solid state. So we can divide solids into two categories: crystalline solids and amorphous solids. Crystalline solids are the ones that have a well-defined shape due to orderly arrangement of their particles. Amorphous solids are the ones that lack orderly arrangement and generally have poorly defined shape. So a crystal is basically composed of particles packed in an orderly three-dimensional array. We call that a crystal lattice. So these are examples of the beauty of crystalline solids. For example, wolfenite has a reddish structure. Barite on calcite has a yellowish structure. Beryl is emerald, has a green structure, which is a common one that you already know. Quartz is also called amethyst, has a purplish structure. Next, let's discuss the types of crystalline solids. So there are five types of crystalline solids. First one is atomic solids, molecular solids, ionic solids, metallic solids, and network covalent solids. Atomic solids are ones that consist of individual atoms held together only by dispersion forces. So these examples of these are metals. Metals are mostly atomic solids. Atomic solids are generally structures with larger structures. They generally have a single atom. Next, you have molecular solids that consist of individual molecules held together by various combination of intermolecular forces. Examples of these are ice. Ice can be considered as a molecular solid. You have ionic solids that consist of a regular array of cations and anions, which is salt is an example of an ionic solid. Metallic solid exhibits an organized crystal structure, which is generally an example of any metal. You have network covalent solids, which consists of atoms that are covalently bonded, but they have a three-dimensional network structure. So when you take cubic closed packing structure of frozen argon, that's an example of atomic solid. So atomic solids generally have dispersion forces. They generally are very soft, have very low melting point, and they are really poor thermal and electrical conductors. Most of them are group 8 elements, which are generally noble gases. And you have molecular solids, which are generally molecules held together by dispersion, dipole-dipole, or hydrogen bonds. They are generally fairly soft. They have a low to moderate melting point, and they have really poor thermal and electrical conductivity. So non-polar molecular solids are oxygen, butane, chlorine. We have hexane and phosphorus. Polar molecular solids are sulfur dioxide, chloroform, nitric acid, water, and acetic acid. Ionic solids are generally due to the particles that are present are positive and negative ions. The interparticle force is ion-ion attraction. Ionic solids are generally hard and brittle. They have a really high melting point, and they are really good thermal and electrical conductors when you melt them. Under normal conditions, they are not good materials, but when you mix them in a liquid or when you melt them, they are really good thermal and electrical conductors. Examples are NaCl, calcium fluoride, and magnesium oxide. Next, you have metallic solids, which have atoms, and the interparticle forces are metallic bonds. They are from soft to hard. They have really low to very high melting points. They have excellent thermal and electrical conductors, and metals are generally malleable and ductile. While ionic solids are hard and brittle, they cannot be made into shape, but metallic solids can be made into shapes. Examples of these are sodium, zinc, and iron. You have network covalent solids, which are atoms, which are made up of atoms, but their interparticle force is covalent bond. Network covalent solids are very hard. They have really high melting points and generally are poor thermal and electrical conductors. Examples of these are quartz and diamond. So remember these two materials, especially diamond. Diamond is called as a network covalent solid because it is a solid that is really strong, provided only having a covalent bond. So a covalent bond does not need to be directly only a gas. It can also be a solid, provided it has a three-dimensional network structure. So these are structures of some of the molecules. So let's try to compare the properties of diamond and graphite. So diamond, if you take graphite, generally has a lesser density. Diamond has very high density. Graphite is very soft, while diamond is very hard. They have the same melting point. The color is around shiny black. Diamond has a colorless transparent structure. The electrical conductivity is very high for graphite. Diamond has no electrical conductivity. The delta H of combustion is minus 393.5. It's about 395.4. The enthalpy of formation is 0. The enthalpy of formation for diamond is 1.90 kilojoule per mole. Now, let's talk about electrical conductivity in a conductor, semiconductor, and insulator. The most common common understanding that we have is the conduction band theory and the valence band theory. So when there is no difference between the conduction and valence band, we consider that to be a conductor. When there is a small energy gap between the conduction band and the valence band, we consider that to be a semiconductor. And when you have a large energy gap between the valence band and the conduction band, we consider that an insulator. So the energy gap actually determines the structure of the material. So with this, we end the lecture on solids and intermolecular forces. So I'll see you again in the next lecture.